Check it out now, y'all.
nanoHUB-U, online instruction.
This is problem number 1 of homework 2. The basic objective in this problem is to get a feeling for how the different distribution functions change with temperature, and also get an idea for how their actual values look like. So in part A of this problem, we are required to calculate the phonon occupation numbers for a couple of different energies and a couple of different temperatures. So the phonons, as you know, follow the Bose-Einstein distribution function, and the Bose-Einstein distribution function is given by this expression over here. So since we know the energies and the temperatures, it's just a simple exercise to plug in the numbers and calculate what the occupation numbers are. So let me just write down the numbers here. So for a temperature of 300 Kelvin and an energy of 0.16 electron volt, the occupation number turns out to be 0.002, and at the same temperature but for a higher energy, the occupation number comes out to be 0.0003. Now increasing the temperature by 10 times and calculating the same values again, we obtain a F of 1.164 for E equal to 0.16 electron volt, and the F for 0.21 electron volt comes out to be 0.796. So there are basically two things that we observe from these numerical values. One, of course, is that the value of the Bose-Einstein distribution function can be greater than 1, which you can see from here. This is expected because phonons are, of course, bosons and are not restricted by the Pauli exclusion principle, and hence can have occupation numbers greater than 1. And another feature to be observed is that the occupation numbers increase with increase in temperature. So this can be understood by just plotting the Bose-Einstein distribution function. So if we plot FB not as a function of energy, so it basically looks like this. It's just a decaying similar to a decaying exponential, although there's a -1 factor in the denominator, and this curve basically shifts upward as temperature increases. So basically, if this is T1, this is for T2, and this is for T3, the temperatures are increasing in this order: T3 greater than T2 greater than T1. So that is the reason why as temperature increases, the occupation of these energy levels increases. So that's about it for the phonons. Now moving on to part B, we are required to calculate the Fermi-Dirac distribution function for electrons in this case. So we basically consider aluminum in this problem, which has an electrochemical potential of 11.7 electron volt, and again the expression for the Fermi-Dirac distribution function is given here. It's similar to the Bose-Einstein distribution function, but instead of the -1, you have +1 in the denominator. But this leads to a very different behavior of the function. Just this change of sign. So again, we calculate the Fermi-Dirac distribution function for 3 different energies and for a couple of different temperatures. Now again, just plugging in the values for the energy and the electrochemical potential and the temperature, we can calculate it from this expression over here, and this turns out to be so at T equal to 1 Kelvin, the distribution function comes out to be 1 for E equal to 1 electron volt, and even for E equal to 11.5 it's 1, and for E equal to 20 electron volt it comes out to be 0, and the same thing calculated at a higher temperature of 3000 Kelvin comes out to be 1 again for the 1 electron volt case, and it comes out to be 0.68 for E equal to 11.5 electron volt, and for equal 20 electron volt it's 0 again. So what you basically observe from this data is that for energies much less than the electrochemical potential, because 1 electron volt is much less than 11.7 electron volt, the occupation is basically 1. And for energies that are much greater than the electrochemical potential, the occupation is basically 0. So and for energies near the electrochemical potential, you basically have an intermediate occupation, which is what you see here for the high temperature of 3000 Kelvin. So, and also just to get a graphical feel for this, we can plot the Fermi-Dirac distribution function as a function of energy, and we mark the electrochemical potential here, mu. So this graph basically looks something like this. So basically, for low energies you have it is 1, and for very high energies it is 0, and it changes from 1 to 0 in a small window around the electrochemical potential, and the width of this window is proportional to the thermal energy. It's proportional to kB into T. It's proportional. It's not exactly that. So basically at very small temperatures, the Fermi-Dirac distribution function is sharp. It's basically like a step function, while at higher temperatures this step function smoothens out and it broadens out basically. Now moving on to part C of this problem. In this part, we are required to calculate the average kinetic energy of argon molecules, and also calculate their distribution, the occupation number, using the classical Maxwell-Boltzmann distribution. So firstly, for a temperature of 300 Kelvin, the average thermal speed of argon molecules comes out to be, if we calculate it comes out to be 398.8 meter per second. So this we need to use the atomic mass of argon, which is 40 atomic mass units, or in SI units it's 6.64 into 10 power minus 26 kilograms. And for this velocity, the average kinetic energy of argon molecules which can be calculated by using the expression half mv square. It comes out to be 0.033 electron volt. Now the distribution that it follows now is the classical Maxwell-Boltzmann distribution function, which is simply an inverse exponential. It's 1 by exponential of E by kB into T. So, and if we calculate this at T equal to 300 Kelvin, it turns out to be 0.28. And moving on to the last part of this problem, we are required to calculate the occupation numbers for photons at 3 different wavelengths. Now, photons are similar to phonons in the sense that they're also bosons and follow the Bose-Einstein distribution function given here. So we are basically required to calculate at a temperature of 5700 Kelvin. So firstly, we need to calculate the energies of these various photons given the wavelengths, and this is simply given by energy is equal to hc by lambda, where c is the velocity of light and it's 3 into 10 power 8 meter per second. So if we calculate that, then the energies for these 3 photons comes out to be 12.42 electron volt and 2.07 electron volt for the 600 nanometer photon, and it is 1.38 electron volt for the 900 nanometers or infrared range photons. And once again, plugging in the energy and the temperature into the Bose-Einstein distribution function, we get the values for the occupation number and it comes out to be 9.8 into 10 power minus 12 for the 100 nanometer wavelength, and it's 0.0148 for the 600 nanometers, and it's 0.063 for the 900 nanometer case. So once again, what we basically see is that the 100 nanometer wavelength is in the UV range and has a very high energy, and so that is basically near the tail of the Bose-Einstein distribution function. And hence the occupation number is really low. It's of the order of 10 power minus 12. And as we increase the wavelength, or in other words reduce the energy, the occupation number increases here. So yeah, there's just another example to show how the Bose-Einstein distribution function varies with energy. And that's about it for this problem.
All right, we're on problem 2.2, and the first part of the problem asks to solve for the partition function, which is kind of a strange name. I don't know where it comes from exactly, but generally speaking, it's a normalization factor. So we had mentioned in the lectures that the probability of some state, we'll call it n, is proportional to e to the power minus beta times the energy of that state. And there can be other terms, but in this case we're using a simple statistics, not worrying about the chemical potential and the number of particles. And here, just so that we can be clear, beta is the inverse of what we've been calling the thermal energy, kBT. And so what we need to do, if each state is proportional to this exponential factor in terms of probability, then the sum of all of those probabilities has to be 1, and the partition function is what we use to normalize. So this partition function is xi, and it was given in the problem. It is the sum over all of these probabilities, or at least factors that are proportional to probability. And if we just do a simple substitution for energy, we're going to sum over all states, and we'll take this summation from 0 to infinity. And we substitute our energy term. That's going to be n, that's the occupation number in this case, plus 1/2, which is the 0-point energy, multiplied by h bar omega, which is the quantum of energy. And it turns out that that summation is a convergent sum, and we can express it analytically, and it makes some sense because as n goes to infinity, you can see that exponential factor will go to infinity in magnitude. So 1 divided by e will go to infinity, and so it will converge. And it turns out that it will give you a numerator that is minus beta h bar omega over 2 divided by 1 minus the exponential factor minus beta h bar omega. And that becomes the partition function. So that's the thing that normalizes our probabilities. For part B, what we'd like to do then is to calculate an average energy. And this, by definition from statistical mechanics, is the partial derivative of the log of the partition function with respect to beta. So beta is that inverse energy, or inverse thermal energy. And so we'll just expand this out a bit. We do the substitutions, and this is the first term minus beta h bar omega over 2, and then we have a logarithmic term that comes from differentiating the denominator of the partition function. And just then going through this and actually taking the derivative with respect to beta, you can simplify this, just doing some simple algebra and arithmetic here. And then we're going to simplify this a bit further. We'll collect all of the energy quanta out in front, and this becomes 1 divided by e to the beta times h bar omega minus 1, so that's all in the denominator, plus 1/2. That is our 0-point energy. And this term, the first term in brackets here, hopefully looks somewhat familiar. That's the Bose-Einstein distribution function, which is the average occupation number. And so this will equal, the simplest way to write this is h bar omega times what we've been calling f superscript 0. That's the equilibrium distribution, plus 1/2. That is the 0-point energy. All right, so that problem is done. All right, we're solving problem 2.3 now. This problem is about phonons and graphene. We've talked a lot about graphene, but we haven't done a lot of analysis of the phonon behavior. Part of the reason for that is that there's a peculiar mode in phonons, and we don't have time in the course to go through all of the details about how that mode originates, but it's called the ZA mode. It's a flexural mode, and it involves out-of-plane vibrations of a two-dimensional material. And so I just wanted to introduce it through this problem. Here we're looking at 3 phonon branches in graphene: the LA, or longitudinal acoustic, the TA, the transverse acoustic, and the ZA. And the peculiarity about the ZA mode is that it has a quadratic dispersion relation near the center of the Brillouin zone, whereas the LA and TA modes have linear dispersions in the center of the Brillouin zone. So they are more like what we do with the Debye approximation. So I just wanted to go through and derive the density of states, and then talk about density of states at particular frequencies. So in general, our density of states relation for phonons, and this is for a two-dimensional material, graphene, is going to equal 1 divided by some length, some characteristic length squared, and the 2 comes from the dimensionality of the material, and then we multiply that by the number of modes, the derivative of number of modes with respect to the wave vector k, and we want to put this in frequency space, so we then do the chain rule and add and multiply the derivative of the wave vector with respect to frequency. So that's really the inverse of the group velocity locally. So if we apply this to the longitudinal mode in its linear region, then we'll find that this will become 1 divided by its group velocity. So it has its own group velocity, which is essentially the slope of the line that we're showing here, multiplied by that L squared factor, and then doing the substitutions of the other derivative of the number of modes with respect to k. That will be L squared times k divided by 2 pi. And then we do finally our substitution, where we substitute our dispersion relation, so that's way up here. We're going to substitute frequency for k using that dispersion relation, and we find that the density of states is going to be proportional to frequency divided by a constant times the group velocity squared. The transverse mode will be analyzed similarly because it also has a linear dispersion relation. So the TA mode will equal frequency divided by 2 pi times the group velocity of that branch squared. And then lastly, the ZA mode takes a little bit more attention. If we substitute, again, that general expression, but now a different type of dispersion relation, we find that the density of states for the ZA mode will look like this. There's a constant C that serves the function of the group velocity, although it is not the group velocity itself. It's a constant that has to do with the curvature of the dispersion relation. So when we go through this, we'll notice that lots of cancellation happens here. The k's cancel, the L squares cancel, and we're left with a density of states that's 1 divided by 4 pi times that constant C, which is related to the curvature of the ZA branch. And so the density of states is a constant itself. So it's somewhat like a two-dimensional electronic density of states, where we had constants for that as well. And the reason that the two things are similar is that we had quadratic dispersion for electrons. That's the normal parabolic dispersion relation for electrons, and so that's why here we have the same thing, a constant density of states. So if we now look at the 3 frequencies of interest, those are the 3 listed here, we see that at omega 1, and I'm going to write this on this side of the page. So at omega 1, the total density of states will be omega 1 divided by 2 pi times the group velocity at 1 squared, plus a very similar term that's from the LA branch, a similar term for the TA branch, and then finally all 3 branches are active at omega 1, and so we have the ZA branch as well, and that's 1 divided by 4 pi times C. At the slightly higher frequency, omega 2, only the TA and LA branches are active, at least the way we've drawn it here. And so we only have the first 2 terms. So the total density of states at omega 2 is simply omega 2 divided by 2 pi times the group velocity of the longitudinal branch plus the same type of term for the transverse branch, but the ZA mode is not active, and therefore it does not contribute anything to the density of states. And then lastly, at omega 3, that's the highest frequency, we have that the total density of states is equal to just the density of states of the longitudinal branch, because that's the only one that is active at that frequency. All right, and that's it for that problem.
All right. In the 4th problem, we will derive Wien's displacement law type of relation for phonons. Now for black body radiation for photons, we know that the solution to the spectral energy density results in the Wien's displacement law, which states that lambda max multiplied by temperature equals to B, or equivalently omega max equals C multiplied by temperature. Here B and C are constants, and lambda max and omega max respectively denote the wavelength and frequency which corresponds to the maximum in the spectral energy density. So in this problem, we will show a similar type of relation for phonons under the Debye approximation. Now, we know that Debye approximation implies a linear dispersion relation with a constant group velocity. Therefore, for phonons in three-dimensional bulk material, the density of states can be expressed as d of omega is equal to omega square upon 2 pi square Vg cube, where Vg is the group velocity. Now, having written the expression for the density of states, we can write the expression for the spectral energy density, which is essentially the energy density per unit frequency. So therefore, the spectral energy density, which is a function of the frequency and the temperature, can be written as a product of the energy of the oscillator, which is h bar omega. So this is the energy of the oscillator, multiplied by the density of states, which is omega square upon 2 pi square Vg cube. So this is the density of states, and this multiplied by the occupation number for phonons, which follows a Bose-Einstein distribution. So this will be 1 upon exponential of h bar omega upon kBt minus 1. So simplifying this expression further, we can write the spectral energy density as U, which is a function of omega and temperature, as h bar omega cube upon 2 pi square Vg cube multiplied by the exponential of h bar omega upon kBt minus 1. Now if I roughly plot the spectral energy density as a function of frequency on the right, it looks something like this. So this is U of omega t, this is omega, where this maxima in the spectral energy density, the frequency at which the maximum in the spectral energy density, that frequency is denoted as omega max. Now we are numerically going to find a solution for omega max. So for a given temperature, the maximum in the spectral energy density will occur when the partial derivative of the spectral energy density with respect to frequency is 0. So therefore, solving this equation, we get the following expression: 3 omega square multiplied by the exponent of h bar omega upon kBt minus 1 minus omega cube exponential h bar omega upon kBt multiplied by h bar upon kBt equals to 0. Now we can simplify this equation further by substituting x star for h bar omega upon kBt, and this will result in the following implicit equation for x star, which will be 3 multiplied by 1 minus exponential minus x star equal to x star. Now this equation can be solved numerically, not analytically, using a variety of numerical packages such as Wolfram Alpha or MATLAB. And if we solve this equation numerically, we get the following result: x star equals 2.82, and therefore h bar omega equals 2.82 multiplied by kBt. Now since this frequency corresponds to the maximum in the spectral energy density from this equation, therefore this frequency is the can be written as h omega max. And this is the expression we were looking for. So you can see from this expression that the frequency at which the maximum in the spectral energy density occurs increases linearly with temperature, or equivalently the wavelength at which the maximum in the spectral energy density occurs decreases with temperature. I will briefly describe a Mathematica CDF tool which plots the spectral energy density as a function of angular frequency, and it lets you change the distribution dynamically by changing the temperature. Now a few assumptions in this model. The first one is the Debye approximation, which was described in the problem itself. The material in question is silicon, which is the three-dimensional bulk material for which the group velocity is 6400 meters per second. And the third important assumption is that the phonon polarization is ignored, which essentially means that the existence of transverse and longitudinal branches are ignored. So the tool which you can see on your screen essentially plots the spectral energy density as a function of angular frequency, and it lets you change the temperature by moving the slider to the left or right. So if I move the slider to the right, you can see the change in the spectral energy density and the distribution. More animation options open up if you click the plus button at the end of the slider, and it also shows you what is the current temperature for which the distribution is being plotted. So if I move the slider to the left, I can decrease the temperature down to 50 Kelvin, and on the right I can increase the temperature down to 500 Kelvin. By pressing the play button, I can let this change dynamically, so you can see that as the temperature increases, the shape of the distribution remains the same, although the frequency at which the maximum in the spectral energy density occurs, that increases. And if you plot the frequency at which the maximum in the spectral energy density occurs versus temperature, we should get a linear sort of a relation which we numerically derived while solving the problem. Thank you.